on element 2 last week. And this week we're going to start, we're going to pick up again with repeaters. So a repeater station, it's more or less just another radio that's set up to pick up radio transmissions on one frequency and send them back out on a different frequency. And usually, or what they call simplex, usually you have two radios. Radio A talks to radio B, and on the same frequency, you both are transmitting and receiving on the same frequency. The repeater makes it nice because a repeater is usually higher up. The antenna is higher up. It can go further distance, but the repeater is going to be transmitting on one frequency, which is the frequency you would listen on, but your repeater transmits on a different frequency. It's what called an offset frequency. I know I sort of messed that up. I apologize, guys. I know how it works. It's just hard to put into words, and I can't just read off a screen. It's just not me. And then they have linked repeaters, and that's really neat. We don't have any, I don't believe, in the ARA right now, but once you, if you link up with a repeater that's linked to another repeater that's linked to another one down the line, you're keying up all those repeaters more or less simultaneously. So what I was talking about, your two radios, that's called simplex. Both radios transmit and receive on the same frequency. In this case, they're using 146.52, and both are using the same frequency for both. The repeater uses what they call duplex. It goes through the duplexer to the receiver, and a duplexer, well, that's a little bit above, but it might be on the test. So a duplexer is a device that permits two signals to run through it at the same time. The signal goes to a controller that offsets the incoming frequency to the transmitter output frequency, which is the frequency that you and I would listen to in the first place before ever transmitting to the repeater. Auxiliary, repeater, or space stations can automatically retransmit the signals of other stations. Going to be on the test, T1D07. The difference between the repeater's transmit and receive frequency, as I was mentioning a little earlier, is called the repeater offset. Listening to the repeater's input frequency is a common use of reverse split function found on VHF and UHF transceivers. Most common repeater frequency offsets in the 2-meter band is 600 kilohertz or 0.6 megahertz, as Steve was mentioning last week. You can have it either way, but 600 kilohertz is most common for the 2-meter band. And for the offset frequency for the 70 centimeter band, that's plus or minus 5 megahertz. And over here, you'll see there are a whole lot of different offsets for different bands. 10-meter band, 6-meter band, 2-meter, 220, 440, and so on up the line. So there are a lot of common things that might happen that could be the reason you're not able to access a repeater whose output you can hear. You could have the improper transceiver offset or no offset. Some repeaters, such as some of the ones that the ARA has, they do require a CTCSS tone to break the squelch. And you could be using the wrong DCS code. That's the digitally coded squelch. We don't use the digitally coded squelch, but some repeaters do. Now, for this question, or this set of answers, all of those are going to be the correct answer when you hit this this type of question. And as I was mentioning, the CTCSS is the term used to describe the use of it's a sub-audible tone. We can't hear it, but it plays nonetheless, transmitted with normal voice audio to open the squelch of the receiver. And your station's call sign followed by the word monitoring, that's what indicates that you are listening to a repeater. It's similar to calling CQ on HF bands. The frequency coordinator recommends transmit and receive channels and other parameters for auxiliary and repeater stations. In other words, they're the organization in charge, so to speak, volunteered, but yet agreed upon to be in charge of setting the repeater frequencies for a given area. I think ours here in our general area is T-Mark. Frequency coordinators, they're selected by amateur operators in local or regional areas whose stations are eligible to be auxiliary or repeater stations. In other words, those who are a repeater station or have a repeater station would be eligible to help select the frequency coordinator. Sending the call sign using CW or phone emission is the method of call sign identification that is required for a station transmitting phone signals. You can certainly use phone, but CW a lot of times is used by the repeaters because it's just a whole lot easier to do, takes up less room, less bandwidth, and is more or less faster too. So here we go into our questions. That was, I was not ready for that. I didn't realize it was going to go by so quickly. Oh, that was fun, Dad. Let's do it again. Did anyone get that or no?
Number C.
Ooh, I know, Bill. I know.
Okay.
I think John knows, though. He'll tell you.
Okay. So what type of amateur station simultaneously retransmits the signal of another amateur station on a different channel or channels? Anyone?
Yes. C.
Okay, very good.
Yeah, I had to unmute myself.
Yeah, I hear you. And I actually went too far here, guys. I went into the pool. So let's go ahead and let me try to do a better job on our next set of questions. I'm just going to go ahead and resume this share and get started with my next set, and then we'll go through that. And then we have, well, I don't have my paper with me.
Comment, please.
Pardon?
Joe, we're not going through question pools in these, are we? Like we're just going through the material.
Correct. We're just going to do the material. Yeah, Bill just advanced an extra slide there. That's okay. But yeah, we're just going to focus on the material in these sessions.
Okay,
yeah.
Very good. Thank you.
Yeah. And Bill, I assume you're, oh, okay, there we go. Sorry.
Okay, sorry guys. All right. So Joe, do you want to stop recording this and then start over again so we have it in a separate section, or are you good to go?
Nope, you can go ahead and press on there, Bill.
Okay, very good. Okay, so this is about emergencies. So we have the amateur radio emergency service. Now, a lot of people might say, oh, ours. No, ARES. We can't read here in amateur radio very well or pronounce things, but that's the way it is pronounced, ARES. ARES is a group of licensed amateurs who have voluntarily registered their qualifications and equipment for communications duty in the public service. Amateur radio operators are well known for their volunteer assistance in emergencies, and they really are very well known. The ARA does a lot of practice drills and more practice drills from the county when they're available as well. But they help out in local problems, 911 problems, Hurricane Katrina, Ida, so on, so forth, all over the place. Amateur radio is extremely valuable as far as being able to throw something together in a heartbeat. An accepted practice for an amateur operator who has checked into an emergency traffic net is to remain on frequency without transmitting until asked to do so by the net control station, unless you are reporting an emergency. There is never a situation, though, when FCC rules do not apply to the operation of an amateur station. FCC rules always apply. Another an acronym, Radio Amateur Civil Emergency Service, or who can pronounce it with me? RACES. A radio service using amateur frequencies for emergency management of civil defense communications. A radio service using amateur stations for emergency and management or civil defense communications, or an emergency service using amateur operators certified by a civil defense organization as being enrolled in that organization. So all of those are relevant and all of those are correct answers. RACES is actually written into Part 97 of the FCC Amateur Radio Service rules and regs, and that it is specified by the FCC for use during a national emergencies. In an emergency, authorized hams participating in a RACES organization may communicate from a police helicopter or a ship or wherever they need to be. Amateur station control operators are permitted to operate outside the frequency privileges of their license, but only if necessary in situations involving immediate safety of human life or protection of property. Now, here we just said earlier that FCC regulations always apply, except for when the FCC regulations have written in exceptions, such as this one. So as a technician, if you are in a life or death or property damage type situation, you need to transmit on something outside, like in a general band, like an HF band. That's an exception. It's definitely not a rule. So the NCS, or the net control station's duties, are to call the net to order and direct communications between the stations that are checking in. Formal messages exchanged by the net station is what we call traffic. The preamble in a formal traffic message contains information needed to track the message, and a characteristic of good emergency traffic handling is passing messages exactly as received. To ensure that voice message traffic containing proper names and unusual words are copied correctly by the receiving station, Such words and terms should be spelled out using a standard phonetic alphabet, which we talked about last week. The term check, in reference to formal traffic message or account of the number of words, a word equivalent in the text portion of the message. And that is the end of the presentation. It was a short one, rather short. My heart is starting to beat a little bit less quickly now. So that is it. We're going to go ahead and move on over to our next thing. Now, I believe that Steve, you're up for weak signal propagation. Is that right, sir?
Yes, that's correct.
All right, I'm going to go ahead and I'm going to, let's see, give up the share. How do I do that? I can resume it. I can do new.
At the top of your screen, it says stop sharing.
Pause share. I don't see it.
Yeah, if you're running off the web, that may not be there. But Steve, I'll tell you what, why don't you go ahead and just try to take command of the screen? Use the share screen
Oh, right
feature
there.
on your.
No, he's right. It was a red button on top of a red background. I apologize. Thank you, Steve.
All righty. Okay. Now, let's see, I will share my screen.
Hey, Steve, before you get started, I just want to give everybody a heads up. A fire alarm went off in my hotel a little while ago. So if I do end up disappearing, that's what happened. I had to evacuate. If that does, I'll try to take my cell phone with me so I can call in or something. But just
Okay.
FYI.
Okay, we got it. Let's see now. What is this now? Get rid of that. And share screen. And we'll start with weak signal propagation. And I'll go to that F5 is a handy button there.
Yeah, it is. It certainly is.
Okay. Let me see. Get this stuff up here. Whatever. Okay, let's let me go to full screen. Come on. Yipe. All right. Sorry about that. Let's see. F5.
There
Okay,
you go.
very good. Say again.
I was just saying, you got it. Go, Steve.
Thank you. Let's talk about weak signal propagation. Propagation means how the wave travels from the transmitter to the receiver, how it propagates. And it's kind of a complex subject matter. Some people make a living off of it. I did for 6 years, and it's very interesting stuff. It's one of the most interesting things I find about radio. It's the application of physics to our hobby here. Here's an example of propagation, transmitter and receiver showing the curvature of the Earth. There are several propagation modes we are going to talk about. Let's start first with the atmosphere. To refract, refraction means to bend, either an optical light beam or a radio wave. It turns out that the atmosphere will refract radio waves slightly so that your radio horizon, that's the distance your signal can travel, is greater than the optical or visual horizon. You see here's this particular station. You normally wouldn't be able to see this guy, but through refraction and other modes, diffraction and scattering, you can reach beyond your radio horizon. So that's a question about visual and versus radio horizon. And because of the atmosphere refraction by the atmosphere, that can happen. It extends your radio horizon. Now, moisture along the path does have an effect on radio signals, but not on the 10-meter and 6-meter bands. It turns out like absorption means where you absorb the signal level, or something absorbs the signal level and weakens it. There is a big fat water absorption line at 22 gigahertz, 22,000 megahertz. And it's not like a brick wall, it trails off from there. But by the time you get down from 22,000 megahertz down to 50 megahertz at 6 meters or 10 meters, you don't have to worry about moisture in the atmosphere. So on 10 and 6 meters, there's very little effect of fog and rain. That's not true, however, at microwave frequencies. Precipitation, liquid water along the path, or water vapor even, it's a weather condition that will decrease your range in microwave frequencies. The water will attenuate the microwave signal. That is a big consideration in satellite communications. So precipitation is a weather condition. Precipitation, liquid water, does affect microwave frequencies. And getting down into the fine print, so does solid water, ice. But that has a different effect. That's outside of our scope here. So water, no problem on 10 and 6 meters, but at microwave, yes, it can have an effect. Now, because vegetation has water in it, you will see absorption on UHF and microwave signals because the signal energy is absorbed and it's turned into heat. What happens is the water molecules are polar molecules, and they vibrate back and forth with the radio signal and they generate heat. That's not on the test. But the point is, absorption is the effect of vegetation on UHF and microwave signals. Not so much at VHF, but UHF and microwave. Signal energy is turned into heat. That's absorption. Now, UHF signals, in the absence of a repeater, a simplex UHF signal is rarely heard beyond the radio horizon, because UHF signals, in addition to the atmosphere, if you transmit upward, the ionosphere can have an effect, but not on UHF signals. See what happens. Let's dwell on this diagram for a little bit. The signal going into the ionosphere is refracted, and this is not the atmosphere, it is the ionosphere. It is a level of the Earth's atmosphere that is above the lower troposphere here, and it's got a lot of ionized particles in it. And radio signals going through that are bent. They are refracted back down to Earth. They do not bounce off like a mirror. It's easy to talk about them bouncing off the ionosphere, but in fact, as they go upward, their direction changes and they're bent back downward again. You can use the word reflected, it's okay, but the ionosphere will do this, but the bending depends on the frequency. The higher the frequency, the less bending. So at higher and higher frequencies, eventually the wave will stop bending and leave the atmosphere, leave the ionosphere. Here's a wave that penetrates the ionosphere. Now the frequency at which this happens, or the angle, this is called the critical angle, where you still get internal reflection back down to Earth. That's the critical angle. You see this blue line here. So this would be a lower frequency signal, and then a higher frequency signal at the critical frequency and the critical angle, and then beyond the critical frequency, it leaves the ionosphere. Now, UHF signals, you usually don't hear them because they're not reflected, or they're not propagated by the ionosphere. The UHF signal will just keep on going and leave. But once you get down to around 50 megahertz, around 6 meters and below, sometimes 2 meters, you will get this kind of an effect. So UHF signals, simplex, are rarely heard beyond the radio horizon. Now, there's other things that go on. Diffraction is where a signal will hit an object, like it's blocking the direct line of sight path between receiver and transmitter, but the signal will curve around this object. It's called knife edge diffraction. And so you can hear, like, for example, where I live, I don't have line of sight to Clear Spring, where the 9.4 repeater is, but I can hit the 9.4 repeater no problem because my signal diffracts over the top of South Mountain. Here's me, and here's the repeater. It's on the other side in Clear Spring. So knife edge diffraction can cause radio signals to be heard in spite of obstructions. Like, here's a microwave signal, and there's a hill. And see how the signal will bend around the hill and over the top of it to a receive site. So that's knife edge diffraction. Another thing that can happen is called tropospheric ducting or tropospheric scatter. If you get a thermal inversion, it will reflect radio signals back and forth to a destination where normally the signal would keep on going to the ionosphere. That's called tropospheric ducting, and it's responsible for over-the-horizon VHF and UHF signals out to about 300 miles on a regular basis. Sometimes when there's a weather front in, where I am here, I can hear FM stations from Philadelphia in around the 100 megahertz range. And that's an example of tropospheric ducting because of a warm air or a temperature inversion. Those of you that were in the military may have heard of tropospheric scatter or troposcatter stations that communicated over very long distances. And this is not on the test, but this is a very reliable mode in some cases where you don't have to worry about what the ionosphere is doing. But anyway, there is a question on the test about tropospheric ducting, and that allows over the horizon communications for VHF and UHF. Temperature inversions cause tropoducting. You can see here warm air and cool air, and the signal it'll act like a waveguide, and the signal will propagate. It'll be guided by the duct, and it'll be guided by the tropospheric duct. And there's another question. A temperature inversion will cause tropospheric ducting. Now, any assembly of charged particles will reflect radio signals, and an aurora is the sun's ionization ionizing the upper atmosphere, and VHF signals will bounce off of that. It's called backscatter, auroral backscatter. Scattering means the signal is not cleanly reflected, but scattered in several directions like a handful of marbles. And you can talk about forward scatter and backscatter. So aurora backscatter can happen, but this is very unstable, and you hear rapid fluctuations, and the sound is distorted too. But that is a signature of auroral backscatter. The auroral curtain reflects radio signals over hundreds of miles when they sound like rapid flutter. Now, another thing that happens is a meteor. When a meteor passes through the atmosphere, it leaves an ionized trail behind it. And that ionized trail, I hear a ding dong. Somebody got a message?
I think Michelle just came back to the group. That was somebody entering the room there, Steve.
Okay.
Yeah.
Yep, I'm back.
the 6
Okay.
meter band, the 6 meter band, meteor scatter is good for 6 meter band also. Let's see. And that's a question. And again, it's because of the ionized trail that the meteor leaves behind it. What's going on? Come on.
Hey, Steve.
What?
I was actually, when I was in the military in the 80s, I was actually part of a group that did meteoric burst communications.
Yeah, the Canadians had a system called Janus, named for the god of the doorway that looks both ways. And that was a military communication system that used meteor scatter. The meteors they're there and they're gone, but there's enough of them that you can establish, if you use error correction, you can establish a digital link over that.
So, a quick question with the ionosphere and the frequency. So, does that mean that an amateur radio operator could actually talk to the ISS because that's in the thermosphere? And if you were at the right frequency, you could actually cut through the ionosphere and actually talk to it?
That is correct. We'll get to that in the next section, but yeah, on
Oh,
VHF and UHF, the ionosphere will not bend you back. Well, 6 meters, yeah, sometimes during high solar activity, but normally you can talk to ISS with VHF and UHF, and their orbital altitude, I think, is only about 300 miles, and the ionosphere goes higher than that.
right.
Let's see. Okay, here we go. So, did that answer your question?
Yes, sir. Yes, sir.
Very good. Now, the ionosphere is a region of the atmosphere that can refract or bend HF and VHF, but not UHF. The UHF will go straight through. And this is not on the test, but I think it's important to understand. Higher frequency means less bending. That's why you get further skip on 10 meters than you do on 20 meters. Because at 10 meters, you have less bending and the signal propagates out farther. And the zone between your transmitter and where you're being received is called the skip zone. But for the basics here on the test, the ionosphere can reflect or bend VHF and and HF radio waves. Here we go. And what happens is the sun will shine on the atmosphere. At night, the ions are all at a high altitude, what's called the F region. But as the sun shines on them, the ionization gets deeper and deeper and deeper. F region splits into two layers, the F1 and the F2 layer. And depending on the frequency, signals will be diffracted at different levels. The D region, I got to quit telling you stuff that's not on the test, but this is fascinating to me. The D region will absorb low signals, like at 80 meters. So that's why 80 meters and 160 meters are no good during the day, because the D region absorbs the signals. But at night, it goes away. That's why you hear AM broadcast stations at sunset, because the ionosphere, the ionization decreases, and you go what's on the right here to what's on the left. But anyway, these are the layers of the ionosphere. So that's too much information, but I don't like just giving facts. I think it's important that I give you understanding. And the ionosphere, again, can refract or bend VHF and HF radio waves. Now, a technician operator has voice privileges, phone privileges only on 10 meters, okay? But if you look, you have CW privileges on 80, 40, and 15 meters. But the question will say, where do technicians have SSB phone privileges? And it's on 10 meter bands, 10 meters only, from 28.3 to 28.5. But keep in the back of your mind, you have CW on 80, 40, and 15. That's a vestige of the old novice class license. Now, a characteristic of HF communications compared to VHF is long distance ionospheric propagation is much more common on HF. So again, HF is more common. VHF often will be above what's called the maximum usable frequency, and it'll go skittering off into the universe. So long distance ionospheric propagation is much more common on HF. SSB telephony can be used in at least some segment of all bands above 50 megahertz. So technicians have phone privileges from 10 meters and 50, 10 meters and 6 meters and up. Now this says in some segment of all the bands above 50 megahertz. That's true, but you also have it in 10 meters. So that's kind of that's an odd way to put a question. But you have phone privileges at 10 meters on up. Now, an amateur station transmitting communications for observing propagation is called a beacon. That's how they figured a lot of this stuff up. Like for a very long time, there have been propagation beacons, and taking measurements of propagation beacons under different situations. Now, most of and those were like in research institutes, but now there are in the ham bands, there are beacon stations in most of the HF bands, and you can listen to them, and that'll tell you what bands are open and which ones are not. This question comes from the rules about what is a beacon, and that's a station transmitting communications for observing propagation or related experiment activities. So high sunspot activity is especially between dawn to sunset. That's when the ionosphere is active or when you can get ionospheric propagation at higher frequency bands. And during high sunspot activity, the ionization is particularly strong. So between dawn and sunset, the ionosphere is very well ionized, and that's the best time to get long distance communication on 10 meters. And that's using the F region, the highest region. And because 10 meters is higher, it's going to bend less, and therefore you get longer skip. But the key here is dawn to sunset during high sunspot activity, you'll get good 10-meter propagation from the F region. Now it talks about polarization. Recall that polarization is the orientation in space of the electric field vector of the radio wave. And if it's oriented parallel to the Earth, it's called horizontal. If it's elevated, or if it's oriented perpendicular to the Earth, it's called vertical. Well, you get a mix of polarizations once you go through the ionosphere. That's not a linear process. The ionosphere is nonlinear. So if you were able to trace out the tip of the E vector of an arriving signal, it wouldn't be horizontal and it wouldn't be vertical. It would trace out an ellipse because the signal is rotating as it comes down. And so you have elliptical polarization. So skip signals refracted from the ionosphere are elliptically polarized. That's why I can transmit in vertical polarization, and somebody in Timbuktu can copy me just fine with a horizontal antenna, because the ionosphere kind of mixes things up. So if you have elliptical polarization, you can receive with either vertical or horizontal. Another thing that happens at 10, 6, and 2 meters is instead of the F layer, you get ionization in the E layer, and it's occasional. It's not a steady thing, but it's called sporadic. Sporadic means it doesn't happen all the time. Sporadic E skip. And you get an occasional strong over the horizon signal on 10, 6, and 2 meters. That's sporadic E. And you see concentrations of ionization here. You have clouds in the E region that will give you that effect. So 6 and 10 meters can provide long distance via the F layer too during this peak of the sunspot cycle. And again, physically, that's because the ionization is stronger at the peak of the sunspot cycle, and 6 and 10 meters will give you long distance communications, and it'll be via the F region. That's in addition to the E skip. See, there's several propagation modes that can happen, but there's the sun. Solar flares and sunspots can also affect radio propagation. Sometimes a solar flare will shut down propagation. Now, technician licenses can use the band at 200 kilohertz between 28.3 and 28.5 for phone operations. The orientation of the electric field is the property of the radio wave that defines its polarization. So here is a visual of a radio wave. You see in this case, the electric field is along the y-axis, which would be vertical. Magnetic field is along the horizontal axis, but it's the electric field that defines the polarization. In this case, it's vertical polarization. Now, a signal that is propagated via the ionosphere arrives by differing paths, and you get irregular fading of signals received by the because of ionospheric reflection. Excuse me. So again, random combination of signals by different paths is likely the cause of irregular fading of signals that are received by ionospheric reflection. So that's weak signal propagation. Are there any questions?
So are all these questions on the technician license, or are they like the higher level licenses?
They're on the technician class license test.
Okay. So
Now,
the
I've given you a lot.
the T3 or the T2, that doesn't equate to the level of the license?
No, the whatever's in your book is the level of your question. Are you saying that some of the more complex stuff I said, is that on the test?
No, like I'm trying to match up on the slides next to a certain paragraph. It would have like, you know, TC T302C4 or something, you know, some type of lookup, FCC lookup for a question and answer. And I was wondering if the T2 or the T3 or the T4 equates to an element or to a level of testing.
No, that's an element. T3 is the third subset of questions on propagation modes.
Yeah.
I'm sorry, I misunderstood.
Okay. So everything that's in this ARRL ham radio license manual is what's on the technician license.
That is correct.
Okay.
Yep.
It's
And-
not divided. It doesn't cover all three of them.
No, this covers only the technician. And
Okay,
of course,
good.
they don't give you all the questions. They just, cherry pick questions from here and there.
Yeah. Just to clarify, in the back of your book, if you're using the ARRL book, I want to say there's a little over 400 questions in the question pool. 35 of those will be pulled for your the exam that you take for the technician license.
Roger that. Yeah, I copy that. And you can download the question pool from the FCC website as well. I was just trying to line up the T1A, T1B, those types of numbers with the test, but he just clarified that everything from T1 to T0 is on the technician level.
Right.
That is correct. Yeah.
Anything with an element beginning with T as in tango will be on the technician. And then they have an E for an extra. It would start, your element was, or excuse me, your question would start with an E or your question number, and then G for general, I believe. So anything that starts with T or is on this slide, this set of slides, gonna be on apt to be on the test, right? Possible. Remember, you get less than 10%, so they throw a lot at you, but it's not really that awful bad.
Yeah, if you go through the questions, they don't plow that deeply. And I hope you don't mind that I gave you some additional background because again, I don't like to just state facts here, memorize these facts. I think if you understand why something happens, it might help you. So please go through the questions and you'll see that they're at a pretty high level. That is not a difficult level.
Yep.
Okay,
And
are there further questions? Okay, let's move on. If I can escape here and go to space. All right, this is about, this is number 11, talk to outer space. In addition to the ionosphere, we deliberately will transmit signals out of the atmosphere to various things that will redirect the signal back to Earth. That's called space communication. That's like having the ultimate repeater on a mountain, like you have something on the moon or something, you know, and you can cover the whole Earth that way. Now, so what is a space station? That is to say, an amateur station in space. Anything that's higher than 50 kilometers above the Earth's surface is considered a space station, according to FCC Part 97. So that's an out-and-out rule, and that's a question. What's considered a space station? 50 kilometers. Anybody know off the top of your head how far that is? Is that like 25 miles or 75 miles? No,
it's about 30.
30 miles. Okay, sorry.
30, yeah. Mm-hmm.
Thank you. Dadgum English system. Okay, so anything that's higher than 30 miles. Here's some, on the space station, they have a very nice ham station on board, courtesy of some of the radio manufacturers. But boy, is that doing a lot of good because school kids all over the world are doing communications with the International Space Station. Now, anyone holding a technician class or higher can make contact with an amateur station aboard the International Space Station. It's called ISS, because they are set up for 2 meters and 70 meters, 2 meters and 70 centimeters. And that's their repeater. I think 2 meters is the uplink and 70 centimeters is the downlink. And so as a technician, you have privileges on 2 meters and 70 centimeters, so you can contact ISS. Now there are different kinds of orbits, okay? And there are, in addition to, ISS I think counts as a LEO. A LEO is in low Earth orbit. And there are all kinds of alphabet soup, and I don't want to confuse you. So the only one I'll mention here is LEO. That's low Earth orbit. And low Earth orbit is like within about 3,000 miles. Geostationary is at 22,300 miles orbital radius. And that's, it turns out that at that altitude, the arithmetic works out where the satellite goes around the Earth at the same rate that the Earth rotates. So from the ground, the satellite appears to be stationary. That's why it's called geosynchronous. Commercial satellites use that. I think there have been some ham satellites there too.
Yeah, very, very few, but there are a couple of them that are way out there. Most of the stuff is in low Earth orbit, though.
Right. And the general case orbit is an inclined orbit. Inclination is how the tilt of the orbit above the equatorial plane. The equatorial plane is a plane passing through the Earth at the equator, slicing it in half. And an orbital inclination is how the orbit is inclined with respect to the equatorial plane. And most orbits are elliptical. And unless you got to fuss it to make it circular, and you got to fire thrusters on the satellite to keep it circular and all of that. But anyway, LEOs are in low Earth orbit. Now, there are satellite tracking programs. It's well defined. The mathematics of satellite orbits are very well defined, but they're also kind of complex. So there are satellite tracking programs. And here's a question off the test. A satellite tracking program will give you a map showing the real-time position of the satellite track over the Earth, and the time and the azimuth and elevation of the start of the orbital pass and the maximum altitude at the end of the pass. The pass means over you, where you can see it from horizon to horizon. So it'll give you all the particulars of the orbital pass, time, azimuth, and elevation. Azimuth, of course, is the direction of your antenna with respect to north, and elevation is the direction of your antenna with respect to local horizontal. And also, there's Doppler shift associated with it, and the satellite tracking program will give you that. We'll say more about that in a bit. Here's an example of a computer program showing the track of the International Space Station. You see this sinusoid here. And that tells you where it's passing. Everywhere under this particular curve at this particular time, the ISS will be directly overhead. And as you get away from this track, you'll have to bring your antenna down from 90 degrees. But this is a track for the ISS. It's an example of the output of a tracking program. Now, to define an orbit, as I said, it's highly mathematical, and there's things called Keplerian elements, named after Johann Kepler, who was an astronomer who figured out how to define the orbits of different heavenly bodies. Turns out there are 8 orbital elements, and they're called Keplerian elements. Those are the inputs. Satellite grabs those and calculates the orbit. Now, a satellite can also carry a beacon, and that contains status information, the health information of the satellite. Beacons are useful for tracking a satellite, but also they give you telemetry, the temperature and the condition of the equipment on board. So a beacon is usually modulated with data, and it gives you status information of the satellite. So that mentions, that's a question also. Now, amateur satellites can use single sideband or FM or CW. Depends on the satellite. All of these choices are correct. It also depends on the design of the satellite.
And what does the CW stand for again?
Continuous wave telegraphy. Continuous wave.
Okay.
Yeah. Morse code.
Yeah, Morse code.
Okay.
The difference here is if the transponder is linear. Single sideband, you need linearity. FM, CW, and data, you do not, because FM and these are not dependent on amplitude. That's not on the test, but that's all. Gee, what's this about? So not every satellite will do SSB. Some of them will only do FM or CW. But all of these choices are correct because it's used by amateur satellites. Anybody, hey, is it legal to receive telemetry? Yeah, it is. Anybody who can receive telemetry from the satellite is allowed to do it. Anybody who can receive the telemetry signal can receive telemetry from the space station. These are handheld antennas. There's a 2-meter antenna and a 440, and there's a handle, and guys do that all the time. They point it, they use a satellite tracking program, and it gives them the local azimuth and elevation versus time for where ISS is going to be, and they point it, and you can listen to the space station, you can receive telemetry, you can talk to the space station. Now,
That's interesting.
yeah, in fact, we were doing that at Hagerstown Community College. One of our guys was running around with an antenna pointing at the sky, and it was really cool because he was listening to ISS. And again, the typical telemetry information transmitted by the satellite beacons is the health and the status. Battery voltage, transmitter power, temperature, stuff like that, so that the people that are tending the satellite can properly command it if there's a problem. Now, a satellite will tend to spin and rotate and other stuff. So, and its antenna will, if depending on the antenna will be spinning with it. And so you can get spin fading where the signal will fade in and out, because in order to receive your linear antenna has to be aligned with the polarization coming from the satellite. And if that gets misaligned, then the signal will drop. There's also Doppler shift. Just like in the sound, as a satellite approaches, the apparent frequency is higher. And the same formula is used for sound as it is for radio. The frequency is higher than overhead. The signal is, there's no shift in the signal. And then the signal is lower as the satellite moves away. So there is Doppler shift. That is an observed change in signal frequency caused by relative motion between the satellite and the Earth station. That's Doppler shift, named after Johann Doppler. And I forget what all he did, but he came up with Doppler shift too. The Doppler effect is the frequency of the sound is heard from a moving source. It depends where you are. Here's a fire truck. And if it's holding still and he blows his siren, you'll hear the same frequency no matter where you're sitting. But if the fire truck is moving, if he's moving away from you, you'll hear a lower. Coming toward you is higher. And then if you're abreast of him, you'll hear the same. If you've ever been to, race cars or whatever, you hear the characteristic like that. That's Doppler shift. Or if you know what a control line model airplane is, that's really obvious. The Doppler is watching control line airplanes. Now, a satellite is not an infinite resource, and you got to be careful of the power that you send to it, because you can mess up other people using it. So a good way to judge if you're at the right uplink power is you should try to match your downlink signal to the power of the beacon. So again, and that's a question, good way to judge whether your uplink power is too low or too high is your downlink signal. It should be at about where the beacon is signal level wise. Because if you use too much power on the uplink, it's going to block access by other users. You're hogging the resource in the transponder, and the transponder doesn't have enough power to go around to all the users. Now there are modes. Was there a question? Somebody said something.
Yeah. For the Doppler, do you have to trim your radio to get a better signal?
Yes, your radio has to correct for the Doppler in one way or another.
Okay.
Yeah. And Steve, you mind if I jump in for a sec?
Sure, go ahead.
Yeah, and as a matter of fact, Steve mentioned that there are programs out there, and many of the programs also, if you have a rig that is compatible with them, a radio that's compatible with them, they will make tweaks to your radio frequencies to compensate for that. Another way to do that is you noticed in the picture that Steve showed a little while ago with a guy holding the antenna in his hand, and he had a handheld radio. What some people will do is they'll literally program in frequencies that match where the Doppler shift will be at various times during the satellite's pass. And they'll toggle through those frequencies. They'll go from frequency A to B to C to D, and that will compensate for that little bit of a Doppler shift. Typically, when the satellite reaches its azimuth, think of perhaps say the ISS, you were lucky and the ISS passed right overhead you, right on top of you. As you point at it, you'd be at the frequency where there is no Doppler shift. That's when it reaches the point where it is literally closest to you.
Okay.
Thanks,
And
Steve.
could we go over the beacon again? How do you know what the frequency of the beacon is? And I'm a little foggy on that, I guess.
It's part of the satellite specs. So you tune where the frequency is and you adjust for the Doppler.
Oh, okay. Gotcha.
Yeah.
Gotcha.
And I'm getting a little ahead of us here. I apologize, but there is a terrific website called n2yo.com. And it's all about satellites, and they've got listing of the ham radio satellites on it. And it shows all of the frequencies for the uplinks and the downlinks, as well as these beacons that Steve's talking about. That's n2yo.com.
Okay.
Thank you.
Okay. Rather than using a bunch of numbers, frequency bands are referred to by letters. Those of you that have been in the military have no doubt heard of X-band radars or S-band, L-band. These are the satellite subbands. They had their origin in the radar bands where they didn't want the bad guys to know the frequencies, so they put letters of the alphabet on them. But these are still used today in satellite communications. Now, these are the frequency ranges for the different bands, and you'll see the HF frequencies. Now, modes, that's in amateur satellite lingo. Mode H is for HF. If you got a mode H uplink, mode V is VHF, mode U is UHF, and so on. So if you're operating mode UV, that's uplink and downlink. UV means you're going up at 70 centimeters and down at 2 meters. That's mode UV. There are some satellites where the downlink is, HF and whatever, but mode UV would be up on the 70 centimeter band and down on a VHF band. And you don't have to memorize all of these. The point is, it's uplink to downlink, and remember the mnemonic UHF and VHF. That'll get you through that question. Okay, that's all, folks. Are there questions? Okay. And next, I guess we got Mr. Bill talking about digital communications.
Yeah, I had to put some eye drops in, Steve. Sorry about that. Okay, yeah, digital communications. So let me go ahead and make a change here. And we're going to use that. And I'll bring this back over here. And go. Where's it at? There we go. And screen share. Boom. And we want, well, before I do that. Sorry, guys. Oh, heck. Yeah. Sorry. There. That's what I was looking for. It got all hidden all over the place. All right, start again. So we're going to show you Mr. Valentine here just for a moment.
Mhm.
I had everything on my large screen, and then I started the presentation, but it wouldn't let me back in. So go in digital. There we go. Again. All right. There we go. Again, apologies all around. Okay, so
No
this is
problem.
the digital mode. Your computer goes ham digital. Going digital. CW is another name for Morse code transmission. Why do they bring CW up here? Because in effect, it really is the first digital type of transmission. It's either on or off. That's what digital is all about. Either ones or zeros, on or off. Continuous wave is on until you key down to turn it off. So it is the first binary type of transmission. And 50.0 to 50.1 megahertz and 144.0 to 144.1, that little tiny sliver of frequency on the 2 meter and 70 centimeter bands are limited to CW only, which is something you should know. And it's nice too, because if you want to do CW and or Morse code and on 2 meters, you always have a place to go. You're not going to find any phone transmissions clogging up that little sliver of it. Now, an electronic keyer is a device that assists in manual sending of a Morse code. You see, this has paddles. So instead of you having, if any of you have seen an actual key, it's sort of like a contraption on a block of wood or slate or something that you had to hit with your fist. Well, maybe I'll show a picture of one of here. But this is a little bit different, makes it a lot easier. I don't know Morse code. That's on my to-do list, however. So if anyone is looking to learn Morse code and needs someone to practice with that also, doesn't know it, hey, I'm your guy. So you can receive audio, and transmit keying. They're all signals used in a computer radio interface for a digital mode. So you have your receive audio, what you would hear, your transmit audio, what you would send, and the keying. When to, in effect, what it's doing is it's telling through an interface, telling your radio when to push the talk button so that what you send can be heard. So here is a diagram over here. So you see this computer and he's tapping away. It's going through an interface. It's called TNC. And then from the TNC, it goes into the radio and so forth. As a power supply, maybe an amp, I don't know. But you could see this graphic matches up to that picture. You have transmit, receive, and a ground going both ways. And then your push to talk and your ground and your audio and your everything's sort of going through, and the TNC does all the heavy lifting. You don't have to deal with any of that. All you have to do is get it set up once, and more or less it's done. So communications using digital voice or data systems via the internet, okay, that's performed with a transceiver and a digital mode hotspot. And this is a digital mode hotspot. More or less, it's a beefed up router that is it's really simplistic, and it does what it needs to do to get the information from point A to point B. And here, that you're not going to need all this for the, if you're really interested, definitely read up on it. I don't feel comfortable in giving that kind of in-depth analysis because I don't deal in that world of digital. I deal in the plug it in, it works world. So all of these are digital communications: packet radio, IEEE 802.II or 11, also known as 802.11, JT65. Now, you'll notice that that is more like a standard. Well, it's your Wi-Fi standard, and it's still a digital communication. It's not saying all of these are amateur radio digital communication modes. It's saying digital communications. Your cellular phone is another digital communication mode. Not amateur radio, still digital communications. Packet radio, IEEE 802.11 and JT65, and all of those it's gonna ask for what are digital communication modes, all of them, and that's element T8 D01. So like I was saying, plug it in and go, more or less connect the computer line in to a transceiver speaker connector when using computer software and a transceiver when operating digital modes. So it goes in the same thing we had up here, radio to the TNC to the computer. And some of these, depending on your radio, depending on your TNC, some of them will connect through your audio out and mic in, or your line in on your computer, depending on what your sound card or your board is set up with. Others, more modern, will just go straight through USB, and the sound card will build into your TNC. So a digital mode capable of operating in low signal noise conditions that it transmits every 15 seconds, and it's really, really fast. And I would say you start with something a little slower like JT65. FT8 is that big brother of JT65. JT65 took a minute per transmission. This cut it down by, a lot, by 4 times. So it's only 15 seconds. 15 seconds on, 15 seconds off, more or less. Can be hard on the radio too. So, I mean, you need to weigh everything. Now, in the station configured to operate FT8, the transceiver audio input and the output are connected to the audio input and output of a computer running WSJTX software. WSJTX software, that's a computer program that is specifically designed by the creator of FT8 and JT65, Joe Turner. That's what the JT stands for in JT65, Joe Turner. And if you're feeling crafty, you can solder up your own connectors. If you're more like me and not really confident in your soldering capabilities, you can also buy one off the internet, and they work just peachy. Operating specialties supported by digital mode software in the WSJT suite are Earth, Moon, Earth, weak signal propagation beacons, meteor scatter, and of course, that is a question in which all of those answers are actually correct answers. All of the WSJT software, and all of these are built in. A lot of other things are built in as well into that software. It's free software. I recommend you download it and take a look when you have some free time. So all of these are correct answers for what may be included in packet transmission. And those are a checksum, which permits error detection, a header, which contains the call sign of the station to which the information is being sent, and automatic repeat request in case of error. And packet's pretty quick too. An ARQ transmission system is an error correction method in which the receiving station detects errors and sends a request for transmission. And that's not specific to amateur radio. That's specific to error detection in general, whether it be on a network or in ham radio like we're talking here. With multipath propagation, error rates are likely to increase on data transmissions because they're a multipath, and we're sort of relying on everything lining back up at the other end successfully, and sometimes it doesn't quite happen that way, and that's why the error rates will increase. An application of APRS, automatic packet reporting system, is that it provides real-time tactical digital communications in conjunction with a map showing locations of stations. Really, really cool setup. Actually developed by a gentleman recently deceased, here in Maryland, close by actually. I can't remember exactly what city or town, but in Maryland. What kind of data that can be transmitted by APRS? So it does mobile tracking. It can track this car. The person has a tracker or the radio that they have in their car, maybe nice car, is built in APRS. That is GPS satellite reads that, which is sending it through the G repeater, which sending it to a radio receiver through a TNC and over to the computer and then over to the cloud. So there you go. There's a lot to it. There is, but once you figure out how to get it working on your station, the rest of this, unless you're really, really super into it, you don't really need to know. It's interesting, but it's not going to be, that depth of the question isn't going to be on the test. Now, what is going to be on the test is that the things that are transmitted by the APRS signal, GPS position, text messages, weather data are all can be transmitted. They don't necessarily all have to be transmitted on every transmission. Depends on what you're sending. The abbreviation PSK means phase shift keying. And this was, when I was still doing digital, my favorite mode, PSK 31. It's like a little chat room in amateur radio. And some higher and more modern transceivers do have a built-in digital interface for PSK and RTTY, radio teletype operation, with nothing else to buy. Others that are a little bit older or modern but not as high-end, you have to buy an interface. Not a big deal. That interface probably, even at retail, is about only $149 or $150. And you can listen to PSK on 14.070 megahertz of an HF radio, and then they have it for 40 meters. And each band has its own little station where PSK 31 and other digital modes sort of reside and hang out. So a gateway, that's the name given to an amateur radio station that's used to connect other amateur stations to the internet. So mobile station area A to mobile station area B, they're connected through, in this case, Echolink software that you can put on your computer, and yes, it's available for your phone now. You go from station A to station B, and no airwaves involved. A little bit of cheating, but it's nice if you want to, let's say, listen to a repeater in South Carolina. Echolink has its places, and it's really cool. Whoever came up with that. Not going to be on the test who that is, by the way. Now, the IRLP, or the Internet Radio Linking Project, is a technique that connects amateur radio systems like repeaters via the internet using VoIP, or voice over internet protocol. And here they're showing you, and you have your transceiver A hitting the repeater, going to a transceiver, going to a computer, going to the internet, and back. DTMF, or dual tone multiple frequency, or touch tone as you and I know it, signaling uses pairs of audio tones. They're also used to control repeater links by the Internet Relay Linking Project. Our repeater with the ARA, it uses some DTMF tones for certain aspects of how we can control our repeaters. Over-the-air access to IRLP nodes is accomplished through the use of DTMF signals. And here are some really nice radios, the Yaesu. And I don't believe I've seen a modern, let's say within the last 15 or 20 years, radio without a keypad. I'm sure back in the day they didn't have one because buttons hadn't been invented yet. Yeah, most amateur radios, including the more in reach radios like the Baofeng and things that are not hundreds of dollars to begin with. Baofeng, Anytone, good for a first radio, but realize it, like everything else, it's only $35 or $40. It's not going to be the best, but it definitely gives you a good jumping off point. So voice over IP, as used in amateur radio, is a method of delivering voice communications over the internet using digital techniques. Antietam cable telephone service, that's voice over IP. It uses the internet to, well, it uses IP technology to take your voice from point A to point B, not going through the regular, necessarily going through the regular phone system. Echolink is a protocol that enables an amateur station to transmit through a repeater without using a radio to initiate the transmission. Again, really nice. I haven't set it up yet, but I know people who have, and it's really cool.
So, hey, Bill, I have a question.
Yes.
Sometimes I don't think very clearly, and I was just wondering, like, using voice over IP over a radio is kind of redundant, isn't it? Like, I mean, can't you're talking over the frequency to talk to someone else, but then you're converting it to a protocol, a SIP protocol type thing to go over the internet, which is what we're trying to get away from.
Yeah, you're 100% correct. But where it shines, right? Where it shines is, let's say, if you want to speak to someone in California. There, remember your VHF signal is only your 2-meter band, your 440 line of sight is it. There's not a whole lot of propagation with 2 meters. So what Echolink and IRLP allow you to do is to talk to someone, you being, let's say, in the general Hagerstown area, to someone in North Carolina, and you're using the internet and voice over IP to take your signal. It hits our repeater. That's linked up through Echolink, and it reaches out to the other other repeater wherever it might be in North Carolina. And then from that point forward, it hits their repeater and goes out in a regular broadcast. But yes, you're right.
So it's basically like a cell tower, but
Yeah,
using different frequencies. I
it's
mean, that's
yeah,
exactly what a cell tower does. It trunks all the
yes,
frequencies down and goes across voice routers across the country, and
yes.
you know,
Right.
okay,
Until it finds the number that it's looking for. Exactly. In this
right,
case,
right.
especially for Echolink, it knows where it needs to go, because you sort of not being I haven't set Echolink up yet, but from what I understand, you sort of pick and choose what repeater you want to go to, and it sort of finds it. So
Thank you.
was that helpful?
Yeah, it just
Yeah.
seems kind of
Yes, it does. But
disappointing, I guess, is the right word. I mean, I want to talk to somebody. I could pick up a cell phone and call them
you
if I
sure can.
want to talk to them over voice over IP, or
Yeah.
use my computer and use a soft phone. But I want to be able to do it radio and M hops and skips and stuff like that.
Yeah, definitely. And that's one reason why I've never set up Echolink. It's like, well, if I'm gonna go to that much problem, I'll just pick up my phone and call. I have a friend, my best friend, he used to live here in Hagerstown. He moved to South Carolina, and that's why I keep bringing up that general area. It's like, I'll just call him, and I agree with you. But at the same time, it's nice to be able to branch out. Remember, you just gotta keep in the back of your mind, amateur radio is vast. There are all kinds of things that you can do, right? All kinds of things. Now, Echolink, even though you're using the internet, you still must get rid. You use your call sign, and you must identify, as well as you must first, before you use it, register your call sign and provide proof of license. In other words, because they're going to Echolink system is going to be retransmitting your voice onto someone else's repeater. You need to first register with Echolink to prove that you are in fact licensed. All right. So I mean, yeah, but I hear you. I do. So just don't deal with it. That's it's that simple, There's plenty of other things in digital modes that you can do without use of the internet at all, really, like JT65, FT8, and many other things in between that I don't. I mean, there are at least 10, maybe more different types of digital modes. A lot of them are available in that WSJT software, JTX software I was talking about. But let's go on and keep on moving forward. So they also, you can also broadcast television over the radio. Analog fast scan color TV signal is the type of transmission indicated by the terms NTSC. And they also have slow scan television, but they're talking fast scan here. A typical bandwidth of an analog fast scan TV transmission on the 70 centimeter band is about 6 megahertz in width. That's huge. So just keep that in mind.
So doesn't that make you a broadcaster, though? I thought in the first class they said you're not allowed to broadcast like music and stuff like that, but this
Right.
is saying you can do TV.
Yes, you can, but you can't do TV as in the sense of rebroadcast a television show. You can point a camera at someone, just like you can point your microphone at yourself and start broadcasting, as long as you are licensed and you are within a specific band within your privileges, right? You can do all that, but you're not rebroadcasting, and you're
Gotcha.
yeah, you're doing it within the
So you could do
FCC.
like a ham radio interview of somebody and broadcast it over the air without fear of being a broadcaster, like a commercial, like a
Well,
podcast or something.
that
No, you can only transmit to another ham.
right.
And you can use Morse code, or you can use voice, or you can use a television signal, but you're
Yeah.
only transmitting to another ham. You're not broadcasting in general.
Right.
But how would I know who was lit? Like, say on the
No.
repeater side, say I was going through repeater and the retransmission frequency, there could be 100 people listening to that. How would I know?
You don't. That's
Okay.
immaterial.
Okay.
Yeah, that I know. It's hard to wrap your head around it, but just like you don't know who you're speaking to when you key down your mic for the first time, but you're actually transmitting to anyone on that frequency who may be listening, right? That's so yeah, it's a little bit for me. I hear exactly what you're saying. But at the same time, it's legal, so we do it.
That's why you also
Yeah.
you got to watch what you say on the repeater, because there's lots of hobbyists with scanners, and you're allowed to receive radio transmissions, but you may not divulge the contents. So you got to be careful about saying, well, I'm going on vacation this next week, because there are people that listen to stuff like that.
Right. Yes, true.
Yeah.
All the time. I mean, I
Yeah.
listen to the repeater just to listen to it sometimes on Saturdays and Sundays and things when I'm doing other things, just in case somebody I want to speak to comes on. But yeah, it's true. You need to mind your P's and your Q's. So I apologize for not having a little bit more in-depth information. Like one of our friends at the club, Bob Law, he considered himself to be an appliance operator, and that's sort of what I fall under. I don't build antennas. I can. I don't make things. I can. It's just not my favorite part of the hobby. I like to do other things instead. But did I leave anyone in the dust? Are there any questions that I can try to answer for people?
Hey, Bill, Joe here. Not a question, but a comment.
Okay.
With some of these more exotic things that we do in ham radio, like television and microwaves and things like that, something else that you may want to know is that a lot of those contacts are sort of prearranged. There are groups that are heavily involved in those types of activities, and they literally will make arrangements, say, off of their website to have their equipment on at certain times. Sometimes they'll have contests and everything, because not too many hams, truthfully, are into it. So some of the things are prearranged, if you will. But as Bill and Steve were saying, it's when you broadcast, and I'm using that term rather loosely here, when you broadcast that video signal, you still have to do things like put your call sign in as part of it. And most likely when you do that, you're going to have a buddy that was prearranged with you that is receiving the signal.
Comment? NTSC has been the standard for color television since about 1953, and it's not used anymore. We're all digital, so you're going to see NTSC equipment starting to dry up. It's the analog equipment. It stands for National Television Standards Committee, NTSC.
Right. That was kind of what my question, what started me thinking. I could see a bunch of pirate TV stations popping up everywhere. If NTSC, because now the FCC doesn't license that anymore. They gave the frequencies to somebody else because we're all digital over the air television now.
Hey, also, I missed a great opportunity when we were talking about voice over IP. I've got my Echo link up on my phone, and I mentioned earlier to everybody that I'm in Reno, Nevada today, and I didn't bring along my handheld with me. But if I want to make a QSO back to Steve or Bill, I literally can do it through my cell phone. And that's where, you know, when we talk about that voice over internet protocol things with interacting with the internet, that's where it comes in. And I got to admit, and unfortunately, for some reason, it won't connect. I think my cell signal in the hotel here is too weak, but it is kind of cool. I mean, I can bring up the local Hagerstown repeater with this thing off of my cell phone, and I could give Bill or Steve a call from it. It's just kind of one of those gee whiz cool things in ham radio.
It is gee whiz cool. It really is. I want to get it set up on my system, but you know, I got way too many things to do.
Yeah. Yeah, and I've got the attention span of a gnat when it comes to ham radio. I just fiddle with everything. That's kind of my thing with it. But that's the great thing about ham radio. There's something in this for everybody.
Right. And
Okay.
and you can do so many things without really leaving amateur radio at all. And it's good for pretty much anyone who's interested at all in any kind of anything technical will find a home.
Right. Absolutely. Okay. All right. If I steal the screen there, Bill.
Definitely, I think it's all
Oh.
yours. I should be stopped.
Okay, very good. Before I start, I see that Kenny and Ken Farmer have joined us. You may be one and the same person. Ken, would you mind coming off mute for just a second and introduce yourself? Okay, nothing heard. We'll come back to Ken. We've got a Ken and a Kenny there. They may be the same person. That's the way Zoom works. But let me go ahead and share my screen. And I'm sharing, and I'm bringing up my presentation, and I'm in the presentation mode. Bill, can you confirm that I am not really broadcasting? Just kidding. And can you see my screen, Bill?
Can, yes, I can.
Okay. All right. I'm going to talk about multi-mode radio excitement. And what multi-mode radio refers to is that most new radios that you can purchase have several different modes of operation that they can operate with. Like in this case here, we've got a really nice ICOM. ICOM is a very, very popular ham radio manufacturer. We've got an ICOM HF transceiver here. And a unit that combines the function of both a transmitter and a receiver is referred to as a transceiver. We've probably said that about 100 times during our talk so far. And some of the various modes you may find on there are, for instance, single sideband is the voice mode most often used for long distance. And earlier, Steve talked about weak signal contacts on VHF and UHF bands. That's single sideband. Now, I may be getting a little bit ahead of myself, but a radio like this will also be able to do CW or Morse code, and it will most likely also have FM capability. And the more modern radios also have special selections on the modes for digital communications as well. And I think it was Bill mentioned that some of the more modern ones, all you have to do is plug a USB cable in from your computer and you can do all kinds of wild digital communications with them. As a matter of fact, I just recently bought a radio like that, and it's a heck of a lot of fun. The primary advantage of single sideband over FM for voice transmissions is single sideband signals have a narrower bandwidth. We're going to get into this bandwidth concept a little bit later on. FM signals seem to typically are broader. Single sideband condenses the power of your radio, if you will, into a narrower bandwidth. A disadvantage of FM compared to single sideband is only one signal can be received at a time. And that is a really big deal with FM, because if you have a bunch of people that are operating on the same frequency, and we talked earlier about 2-meter FM, 146.52, if you have a bunch of people that try to transmit at the same time, only the strongest signal will go through. And by the way, this is not on the test, but this is the reason why airline flights, you know, the flights used by commercial airplanes and actually civil airplanes and things like that, they use AM. For that very reason, that if somebody was calling out a mayday or declaring an emergency or something like that, if somebody else was talking using FM with a stronger signal, it'd totally wipe them out. But using AM, oftentimes a weaker signal can be heard in the background while somebody else is transmitting. That's not on the test, just an FYI. Okay, Let's talk about single sideband. Single sideband is the most popular form of voice communications on shortwave broadcasts. And those are the ones when we talk about places like 80 meters and 40 meters, it's everything at 6 meters and above that spectrum there. And how single sideband works is when you transmit a signal, it consists of a carrier wave. Like this is a CW or a Morse code signal. And you can see it's very narrow and very distinct. When you broadcast an AM signal, and this is like the AM that you would get off your car radio, you can see you've got a carrier signal in the middle, and off to the sides are two what are called side lobes. This is where the intelligence is. The carrier portion in an AM signal more or less just goes along for the ride. But the intelligence, in other words, like as I'm talking to you now, if I was doing that over a single sideband radio, all that information, all that, bear with me for a moment. Okay, all that information would happen in these sideband lobes off to the side. Well, some smart person a long time ago figured out, hey, why don't we filter out the carrier and one of the sidebands and only focus on one of the sidebands, single sideband radio? The beauty of that is that in a configuration like this, you waste a lot of your transmitted energy in a carrier signal and also in a sideband you really don't need. Single sideband puts all of the power of your transmitter into that intelligence you want to broadcast. And that is why single sideband has become the standard in shortwave communications and is actually used a great deal as Steve was talking about, satellite communications uses sideband. And actually there's some sideband operation that goes in the VHF and UHF realm as well. Upper sideband is usually used for 10-meter HF, VHF, and UHF single sideband communications as our communications mode. That's what you need to know as a technician, because that's where you're going to be utilizing upper sideband. You'll only have privileges on 10 meters. However, upper sideband is also used at all the frequencies above 10 megahertz. So like, for instance, if you go on the 20-meter band, which is at 14 megahertz, or the 15-meter band, which is at 21 megahertz, you'd be using upper sideband there as well. If you're on 40 meters and below, which is around 7 megahertz, you would use lower sideband. The function of the single sideband CW FM switch on a VHF power amplifier is to set the power amplifier for the proper operation in the selected mode. This is kind of a little bit of a goofy question, so it's one of those ones that you'll probably just kind of need to commit to memory, but that is important in the utilization of a VHF power amplifier, because the power amplifier is going to be configured and operate differently for single sideband and CW than it will for FM. We won't go into the details of this right now, but that's just something you want to know. That's the function of that switch. Now, here's a question that I kind of wish I had presented to you a slide or two ago. Modulation describes the combining of speech with an RF carrier signal. That was probably the first thing I should have talked about in this presentation, because modulation is what we're talking about when we talk about FM, sideband, AM, all of those things. And once again, it is the idea of taking a carrier signal of some type and altering it such that you sort of, if you will, put intelligence into it. You put the sound of a voice, or you can use this type of methodology for digital communications. So over here on the right, you can see they've got an indication there of amplitude modulation. And the modulated result down here, as you can see that the signal, the carrier is a nice steady sine wave, but when you modulate it, it modulates up and down. The carrier goes, the strength of the carrier or the amplitude of it varies. With frequency modulation, once again, you've got a nice steady carrier, but when you modulate, the frequency changes. So you can see here how the sine wave gets crunched together at times and expanded at times. That's how FM works. You modulate not amplitude, but you modulate the frequency. And in digital communications, you do similar things also. Usually things like, as Bill mentioned, frequency shift keying. Once again, you start with a nice pure carrier wave, And what you do is you then again alter it. You alter the phase of the signals that are going through it. And those alterations of phase represents either ones or zeros in terms of the digital communication you're sending. Okay, 3 kilohertz is the approximate bandwidth of a single sideband voice signal. Period. Just something you got to know. If you're ever wondering what the bandwidth is of a single sideband voice signal, it's about 3 kilohertz. And that's something that you could see on the test. Now over here, they're showing a picture of a Yaesu brand crystal filter. This filter here operates with a center frequency at 9 megahertz, and it has a bandwidth of only 3 kilohertz. And things like this are used to differentiate, to allow, once again, those sideband frequencies to go through. Now, this description over here, this depiction is trying to show that, for instance, when you're operating on upper sideband, when you modulate a signal, say 21.275, which is the lower end of the general class phone band, the frequency increases as it is modulated. So it goes from like 21.275 maybe up to 21.278 or something like that. Now, why is that important is because if you're operating up at the high end of a band, if you modulate that signal on upper sideband, your intelligence, the signal, the bandwidth of your signal may go out of the band. So, in previous lessons, we've talked about how, you probably don't want to operate at the very edges of the bands that you're authorized to be in. This is the reason why, is because when you modulate things, the frequency bandwidth of those signals will change. Okay, the RIT or clarifier could be used if the voice pitch of a single sideband signal returning your CQ call seems either too high or too low. RIT means receiver incremental tuning. That is a fancy word for fine tuning. On this radio that they've got over here, you see they got a big tuning knob over here to the right. And that is used for, shall we say, the more coarse adjustments of getting your frequency. If you tune to a frequency and you hear somebody talking out there and their voice sounds funny, you can use the RIT, the receiver incremental tuning button, to fine tweak it. And that is a fine adjustment of that received frequency just to bring their pitch in range. And oftentimes those are associated with a button. You can turn this feature on and off to do it. In this particular radio here, you see in the lower corner here, there's actually a button on an ICOM 730 to enable that feature. A lot of times you don't need to do that. I find myself hardly needing to do that type of work on my new Yaesu radio, but it is a very common feature in HF sets. The name of a circuit that generates a signal of a desired frequency is called an oscillator. And over here, they've got a couple of pictures of them. And this one here is controlled by a crystal. Even today, crystals are very, very common in our radios, quartz crystals, because they are very, very stable. When you tune them for a particular frequency, they stay at that frequency. They're, the term is they're rock solid, no pun intended. But this is a test question that you could see. The name of a circuit that generates a signal of desired frequency is called an oscillator. The type of emission that has the narrowest bandwidth is CW. That's Morse code. And this is a nice little depiction over here. They've got some of the different modes of operation. CW or Morse code requires very little bandwidth. You can see only about 150 hertz, which really isn't much in the radio spectrum. Single sideband, everybody should know this now, you can expect that to be about 3,000 hertz or 3 kilohertz. An AM transmission in ham radio requires about 6,000. And that's why I was talking before. An AM signal, you're requiring all that additional bandwidth, whereas with single sideband, you can condense that into a smaller package. And typically, you're going to get greater range and greater voice power, if you will, out of it. And then for FM, your signal bandwidth could be anywhere from 5,000 for narrowband FM to 15,000 hertz for wideband. And those are typically, most of your operation for this you'll find is on those VHF and UHF radios that we've talked about previously. Okay, I'm going to take a short break for a sip of water. Does anybody have any questions so far? Okay, moving on. How are we doing for time here? Okay, I got to pick up the pace a bit. Okay, as I mentioned before, 150 hertz is the approximate maximum bandwidth required to transmit a CQ signal, and that is on CW. That's the Morse code CW. Excuse me. 2400 hertz receiver filter bandwidth provides the best signal to noise ratio for single sideband reception. Now, before we were talking about how a single sideband signal occupies about 3 kilohertz. Well, they're saying here that, you know, if you were to use a filter of about 2400, that would take a little bit off of the total range of that, but that is going to provide you with the best signal to noise ratio reception for single sideband. And they've got a depiction here that shows what the bandwidth of that would look like. By the way, on here, they also show points on here where it is negative 3 dB. Negative 3 dB is the point where about half of the power of the signal is gone. But that is how we define the passband or the bandwidth of a filter. They often refer to it as the 3 dB point, or 3 dB bandwidth is referred to that. I don't believe they'll ask you about 3 dB specifically on the test, but that's where that comes from. But the number that you need to remember for that particular question is 2400 hertz. The advantage of having multiple receive bandwidth choices on a multimode transceiver as it permits noise or interference reduction by selecting a bandwidth matching the mode. Yeah, modern transceivers have varying bandwidth, and if you have interference that's coming from either side, or if you have some noise on it, you can select different bandwidths, or some of them have continuous adjustment of it to eliminate that noise. Sensitivity is a term that describes the ability of a receiver to detect the presence of a signal. Sensitivity, please remember that word. So how sensitive is a receiver is its ability to detect the presence of the signal. Now, another term you're going to see is selectivity. We're going to get that in a moment. A mixer is used to convert a radio signal from one frequency to another. And in this here, they show a mixer as just being a proverbial black box, where signal A comes in at 800 hertz, signal B comes in at 1250 hertz, and the output is 455 hertz. That is true, but in a mixer also, you will get both the sum of the frequency and the difference. So in this particular depiction, something else that will come off the mixer typically is also here, it took the difference of the two. 1255 minus 800 is 455, but you would also get 1255 plus 800, which would be 2055. And the way that you differentiate one from the other is over here, and they show this in a depiction later on as you put in a filter to filter out either the higher frequency or the lower one. The term that describes the abilities of a receiver to discriminate between multiple signals is called selectivity. And once again, if you've got interference coming on either side of your frequency bands or something like that, having a good selective receiver, one with good high quality filters, will allow you to filter out signals that you don't want to hear and zero in on the one that you want. And again, that term they're looking for there is selectivity, as opposed to sensitivity that we talked about earlier. An RF amplifier is commonly referred to as the front end of a receiver. You can see they've got an RF amplifier, and the question associated with this is an RF preamplifier is installed between the antenna and the receiver. Now, this amplifier is commonly built into higher quality receivers, so that's not something that you have to go buy separately. That is part of your receiver. And here they show a mixer. The signal comes out of the RF amplifier, and then an oscillator mix them together. And in this one here, they show the filter. Once again, you're going to get the plus and minus of these two signals coming out of a mixer, so you got to filter them. And then there are phases of amplification and demodulation that happens. And hopefully at the end of it, you get something coming out the other side that either sounds like a CW signal or somebody's voice. A transverter converts the RF input and output of a transceiver to another band. These are neat little things. And what this will allow you to do, in this case here, they show a 2-meter transceiver that is converted to a transverter that operates at 1296 megahertz, up slightly above a gigahertz. As a matter of fact, a while ago, Steve lent me, he had a transverter for 6 meters that he lent me. They're cool little things, and what they do is they expand the capabilities of your receiver, your transceiver, to bands you might not otherwise be able to operate on. A technique for time multiplexing 2 digital voice signals on a single 12.5 kilohertz repeater channel describes DMR, or digital mode radio. Before I get heavily into this, I'll apologize a little bit. There are several questions in here about digital radios, and digital radios are a little bit of a niche. So we are going to cover these. You may want to come back and watch the video on this again. Digital radio is a pretty cool thing. I'm just getting into it recently, but it's one of those little niches in ham radio. It's not, there is a lot of capability out there, but most of the stuff that we do is on analog FM. So just FYI. But the technique for time multiplexing, which is using time to differentiate between 2 digital voice signals on a common frequency, is referred to as digital mobile radio. Color codes are used on digital mobile radio repeater systems, or I should say codes used on DMR repeater systems, much match the repeater code for access. And this is a methodology of just limiting access to particular repeaters. So what they do is they have these access color codes that they use for that. You program that into your radio, and your radio will be able to hit the repeater. I apologize, I keep flipping sides unintentionally. To join a digital repeaters talk group, you must program your radio with a group ID or code. And the group ID is quite simply that. It is a number that you would program into a DMR capable radio. And again, I know these questions are a little kind of weird, if you will. They're very specific to this. We will go over these again when we get to Cramfest and everything, and you'll see them in there. But, truthfully, they're just kind of these little things that, you're just best to commit to memory. And, hopefully you'll be able to get past them to, on the test if you do see a question about them. A talk group on a DMR digital repeater is a way for groups of users to share a channel at different times without being heard by other users on the channel. Yeah, this is a methodology of having two conversations going on the same radio without interfering with each other. And that is actually a pretty cool thing about digital operations. The DMR code plug contains access information for repeaters and talk groups, i.e. channel information, contact list, radio buttons, all the necessary channel informations and things of that sort, all the operating parameters. And this is something that just gets programmed into a digital mobile radio so that you don't have to punch that information in every time that you go to a particular repeater. A specific group of stations can be selected on digital voice transceiver by entering the group's identification code. And we talked about that previously. Once again, that's a number that would be programmed into your radio that would allow you to enter that particular group. And again, don't feel too bad about these if I just kind of blew you away with them. We will have opportunities to review these again. And unfortunately, there are some things in ham radio that it's just kind of best to commit to memory for your exam. Your call sign must be programmed into a D-Star, that is digital smart technology for amateur radio, digital transceiver before transmitting. My new radio has this capability, and I will say that this is pretty cool because I can hear people on a local repeater that are having conversations. Like there's a guy in Great Britain who very commonly has a morning QSO with a friend of his in Japan, and you can do this over. You can hear this on local 2-meter radios. It's really cool. But these are enabled and they are connected to the internet for that capability. And for everybody, I apologize. I am running long here. I'll try to pick up the pace as best I can, but please hang with me if you can. An amateur radio-based data network using commercial Wi-Fi equipment with modified firmware best describes what an amateur radio mesh network. Bill mentioned this a little bit earlier. That's the idea of using those hotspots and stuff. But yeah, you can literally take Wi-Fi transceivers and create in ham radio your own little mesh network. Now, granted, these things have to be fairly close together, but you can use these. You can put several of them in coordination with them and create a wider area network with it. I don't know anybody who does that, but it is a possibility. So I did go through that kind of quick. Before I move on to the next topic, is there any questions about multimode radio excitement? Okay, I hope everybody's hanging in there with me. And we're on to our last topic, so hang in there, everybody. And here we go. And slideshow. And Bill, if you can confirm that you're still seeing my slides.
I am, sir.
Okay, let's run some interference protection. Okay, it is very common in ham radio, because we're dealing with transmitters, for things to interfere with our radios and for our radios to possibly interfere with other things. And this is kind of a big deal because, there are FCC rules about this. So we need to know what to do if we experience these problems. Possible problems if you receive a report that your audio signal through a repeater is distorted or unintelligible is that your transmitter is slightly off frequency. Your batteries may be running low, or you could be in a bad location. All of those answers are correct, and that's one of the questions out of there. So once again, if your audio signal through the repeater is distorted, those are the things you want to check. If a transmitter is operated with excessive microphone gain on single sideband transmissions too high, it will result in distorted transmitted audio. That is true of both single sideband, but that is also true of FM. So yeah, if you have got excessive microphone gain or you're speaking too loudly into the microphone, it's almost kind of common sense. It could distort your transmitted signal. So some things to do to prevent this is talk farther away from the microphone if you're told your FM handheld or mobile transceiver is over-deviating. Over-deviation will come in the form of, that means that the frequency is becoming too wide and you'll get a distortion, almost like a buzzing type sound associated with your transmission. If you're talking too loudly, your transmission might break up on voice peaks. That's another thing that could happen. On the peaks of your transmission, there could be distortion. The scanning function of an FM transceiver tunes through a range of frequencies to check for activity. Yup, just like buying a police scanner, you can also set up your FM handheld such that it goes through your local favorite frequencies. And if anybody's broadcasting on them, it'll usually park on that. Well, it will park on that frequency for you, so you can call that person back. Be sure that all TV feed line coax connectors are installed properly as a first step to resolve non-fiber optic cable TV interference caused by your amateur radio transmissions. Yeah, if your ham station is interfering with your TV, that's definitely something you want to do, is go and check all of those connections. There are some other things you can do, but this is the easiest and a very common problem. Causes of radio interference include fundamental overload. Fundamental is your primary frequency. Harmonics. Harmonics are even digit multiples of the frequency that you're operating on. And spurious emissions. Spurious emissions, just like spurious, it's perhaps somewhat random, but it could be caused by problems with your radio. So radio frequency interference can be caused by any one of these. All of these answers are correct. And that is question T7B03, by the way. Reports of garbled, distorted, or unintelligible transmissions are symptoms of RF feedback in a transmitter or receiver. So again, if you do get a report that you're garbled or distorted, one of the problems could be is that you're getting, your RF is creating a feedback loop within your shack, within your transmitter or receiver. A reason to use shielded wire is to prevent coupling of unwanted signals to or from the wire. And that's why coaxial cable is so popular in radio applications, is because you've got a center conductor that's surrounded by metal fiber wires, and that provides a shielding to prevent interference either coming into the wire or coming out of the wire, for that matter. If a neighbor tells you that your station's transmissions are interfering with their radio or TV reception, make sure your station is functioning properly and does not cause interference to your own radio and television when it's turned on to the same channel. That's probably the first troubleshooting thing that you want to do. Not as common in the days of cable television, but it could happen, especially if you got a neighbor that's using a conventional TV antenna. If a broadcast AM or FM radio receives an amateur radio transmission unintentionally, the receiver is unable to reject strong signals from outside the AM or FM band. This is kind of pointing the finger at the radio itself. A poor quality radio, like a cheap AM or FM radio, may get overwhelmed by an amateur radio transmission. There's not too much you can do about that except to perhaps isolate that radio, but there may be some things you can do in your shack as well. But in this particular case here, they're just saying that the receiver may not be able to reject the stronger signals. To reduce or eliminate interference by amateur transmitter to a nearby telephone, put an RF filter, which can come in the form of a ferrite choke, on the telephone. And you can see these can be purchased online on the internet. Overload of a non-amateur radio signal or TV receiver by an amateur signal can be reduced or eliminated by blocking the amateur signal with a filter at the antenna input of the affected receiver. And this here is a little TVI filter, and these can be purchased as well to eliminate that type of interference. And these usually, by the way, are not very expensive. We're talking a couple of bucks, but sometimes if you've got an interference problem, these are the things that can fix it for you. A band reject filter can reduce overload to a VHF transceiver from a nearby TV broadcast station. And what these are is they come in the form of either a low pass, a high pass, a band pass, or a band stop filter. A low pass filter allows frequencies below a particular frequency to pass. A high pass filter allows frequencies above a particular frequency to pass. A band pass has both a low and a high, and a band stop filters out. Let's say the frequency that was causing your interference was right in the middle here. The band stop filter would nullify that. It would take it out. And these over here are more, shall we say, drastic or digital depictions of the same thing. But they do show here, for instance, a cutoff frequency. Unless you're using digital signal technology, though, you're not going to have something that's that abrupt. It's usually a more graceful tapering down. If something in a neighbor's home is causing harmful interference to your amateur station, what you want to do is work with your neighbor to identify the offending device. Politely inform your neighbor about the rules that prohibit the use of devices which cause interference. Check your station and make sure it meets the standards of good amateur practice. So all of these answers here are correct. And this kind of falls into the common sense thing. You know, if a neighbor is something that somebody's got over at their house is causing interference, you know, be neighborly, go over and talk to them about it, and hopefully you can come up with a good solution for it. Okay. So that was run some interference. I apologize for going through it kind of quickly there, but are there any questions on this topic, or for that matter, anything we talked about today? Okay. I want to thank everybody for calling in and being part of this. You folks are going to have a great heads up as we go into Cramfest. So please hang with us. I know that this can be a little bit overwhelming, but trust me, if you stick with us, if you come to us and be with us on Cramfest, you're going to find passing your exam is going to be much easier by virtue of the fact that you did put this extra effort up front. Also, I'd also like all of you, if you happen to have friends who might be interested in ham radio, please ask them to reach out to us or point them towards the Antietam Radio Association website. We'd love to have more folks involved in this. We're hoping for a good turnout at Cramfest, and you know, we'd welcome, of course, more people on these weekly study sessions as well. I sent out slides earlier, the Ham Radio 101 slides, and in there is information about getting your FCC FRN number and things of that sort. I did give some extra information about that in the form of an email. Please go take a look at that. You will need your FRN number when you come to take your exam. It's real easy to go in and sign up for it. Doesn't cost you anything, but go ahead and get that number. Go ahead and get registered with the FCC. Also, there's a slide in there about ARRL exam practice sessions. You may want to go ahead and sign up for that. I don't know if you're ready right now to go ahead and start taking a bunch of practice exams, but I'll tell you what, after our next class, it's probably time to start to jump into that and go ahead and get as many practice exams under your belt as you can before Cramfest. So again, thank you so much for being with us. Steve, Bill, any closing comments for the group?
No, not at this time. No, sir.
Just a point of trivia. You talked about digital mobile radio and multiple users sharing the same channel at different times. That's called time division multiplex. Some of the military folks might have heard that before. TDM, time division multiplex.
Mm-hmm.
That's not on the test, but that's the technical name for it.
Okay, wonderful. Okay, thanks, Steve. Okay, any closing comments from our students?
Well, just thank you.
Yeah, thank you for the information.
Well, thank you all for being here. I hope you got a lot out of it. Hang in there with us. I mean, we know that this is a kind of a fire hose effect and everything, but trust me, this will pay big dividends for you when you all have your license. So, okay, we held you kind of long here. I do apologize for that, but we did cover quite a bit of ground tonight. So everybody have a terrific week. Please too try to stay in the books a little bit about this, and we'll see you all next week.
Have a safe trip back, Joe.
Will do.
Yes.
Thank you, Steve.
Good night, everybody.